Hi class, welcome back to the continuation of our lectures in quantum mechanics. And our main reference again is Introduction to Quantum Mechanics by David J. Griffiths. I recommend you that you get a hold of this book because it's very important to help you in this lecture series. So this is the beginning of another chapter, and in this chapter we'll be discussing about quantum mechanics in 3 dimensions. So um, we know that the Schrodinger's equation is of this form, and and here the psi is the wave function and the h is the Hamiltonian. The Hamiltonian operator h is just taken from the classical total energy h equal to kinetic energy plus potential energy. This is the kinetic energy and this is the potential. So the kinetic energy could be written into in terms of momentum, and the momentum is prescribed as a first order differential with respect to a coordinate in the in quantum mechanics. So for the for this component, you have the momentum as h over I partial with respect to x, and for this for y in the direction y, h over I partial with respect to y, and for the z direction it's h over I partial of z partial with respect to z. So that is the um, equivalent in quantum mechanics. So this time we're taking the momentum in 3 directions. So we can write the momentum into this one here. H bar over I times the del operator, where the del operator is just equal to this one. In Cartesian coordinate will just be partial of x times I plus j partial with respect to y plus k partial with respect to z. So our Schrodinger equation would now look like this here. And the Laplacian, the square of the del, would now look like this. You don't have direction for this anymore because this is the Laplacian is just the dot product of del and itself. So the direction will cancel in the dot product. So the potential V will now be functions of x, y, z, and t. So the wave function and the potential energy will be functions of x, y, z, and t. And the probability of finding the particle in the infinitesimal volume d cube, d cube, this is the product of dx, dy, and dz is just equal to this. And of course, if you integrate that, that should be equal to a constant, and if it's equal to 1, that's called normalization condition. If it's not equal to 1, then you just, if it's equal to a constant c, then you have to divide this with then psi should be divided by square root of c. So anyway, um, um, psi square is equal to psi star psi, or equal to psi star. This integral is calculated or integrated all over space. So if you talk about complete set of states, you can in complete set of states, we can actually do also stationary states, and the stationary states is given by this one. This is the time independent Schrödinger equation for the 3 dimensions. This is just the same as that of the one-dimensional Schrödinger equation, but you just have your p to be replaced with this one here. So that's just the replacement of p square, and I mean that one. Your complete set of stationary states would be written in this form. Here, this is your psi, it's a function of r and t, and this is your phi, it's a function of r, and this is your exponential of the energy. So anyway, the general solution would be, because each of the stationary states would contribute to the general solution. So your wave function this would contribute to the general solution to the time independent Schrödinger equation. So each of the stationary states would have contribution, and the contribution would be determined by the constant Cn. If the potential admits continuum states, like the wave packet, for example, then yeah, phi would be in the form, the psi I mean, would be in the form of integral. This would be an integral if it's continuum, the energy is continuum, or yeah, or it's is determined by a continuum variable. So here, for the spherical coordinates, radius r and polar angle and azimuthal angle phi, polar angle theta, determines the point in spherical coordinates here. So it would be easy or easier to solve the Schrödinger equation using spherical coordinates in this case. Typically, the potential is a function of distance from the origin. In this case, it is natural to use the spherical coordinates r, theta, phi. So in this case, we have to use the Laplacian in spherical coordinates, and this is just the form of the Laplacian. And the time independent Schrodinger equation becomes this one here. So since we're looking for separable solutions, we can separate the radial and the angular part. So we can make this a product of r and y, where r there is just a pure function of a radial function and the y is just a pure angular function. So we can replace the phi with ry, and so the Laplacian of, or the Schrodinger equation would look like this now. And yeah, these are the y and the r. So the y gets out of here because this is only differential with respect to r. And this one, you can take r out because y is only variable with with respect to angular variables theta and phi. So if you divide by yr and multiply by negative 2mr squared over h bar square, you will reduce the Schrodinger equation into this form. So this is now the equation, and this one here, this first term, is a function of r, and the second term is only a function of theta and phi. And looking at this, you have two terms which are of different arguments, angle and radial arguments. So you can let them equal to a constant by the rules of partial derivatives. So you can let a separation constant L times L plus 1 to be equal to this term, and then you have negative L times L plus 1 as for this term, because they have to add up to 0, so that's why the other one is negative. Here they have to add up to 0. So the angular equation is this one here. You can simplify by multiplying y sine square, so this is now the angular equation. And you can further divide or separate the angular part into theta part and phi part, so that you will have a product of theta function of theta and phi function of phi here, and you plug in here to no, you plug this here, this one, plug this here, so that you will arrive at this expression, and by dividing theta and phi. So again, each of this term, because this one is only a function of theta, and this one is only a function of phi. So each of these must be equal to a constant 2. So we let the constant to be equal to m square. By the choice of a constant, don't worry about it. You will see why it's m square, not m. But yeah, later you will find out why. Anyway, so the first time would be equal to m square, and the other term should be equal to negative m square, because they have to add up to 0. So you can now get the solution. The phi equation is it's like trivial because we know the solution of this. This is just equal to if you solve this one, this is just this one would just be equal to this expression, and then when you integrate twice with respect to d phi, you will get phi equal to this. M is, I mean, phi of phi is equal to exponential of I m phi. There's actually two solutions. The other one is negative e to the negative I m phi, but we accommodate all the m's from negative m, or we include m, or we run m from negative infinity to positive infinity, so that we can just write this simply. So also there's a constant here. But let's let that constant be absorbed with a constant of phi, so that it would be simpler. So if by the way, here you have exponential as a solution of phi, because we don't necessarily require that the solution to be real. In the case of electrodynamics, the solutions have to be real. That's why you have to use sines and cosine there. You can review your special techniques in electrodynamics and check that the solutions for this one is in terms of sine and cosine. Now again, take note that phi of phi plus 2 pi is just equal to phi of phi. It goes back after one revolution. In other words, exponential of im phi plus 2 pi is just equal to exponential of im phi, or exponential of 2 pi im is equal to 1, and this will tell us that m must be an integer. So m runs like an integer, so 0 plus minus negative 1, and it goes to positive negative 2, and so on. And this is called, by the way, the magnetic quantum number, n. For the theta equation, you have this one, this expression. And the solution for this is just of the form, this is the function. You can review your electromagnetism and check that the solution of this differential equation is an associated Legendre function. You actually have you actually have done in your electromagnetism in solving the Laplace's equation, and you got their Legendre function. It's also the same solution for this equation here, for this differential equation, I mean, here. So the PLM, or the PLM or PML, whatever you call it, or this is called the associated Legendre function, and this is defined by this expression here. And the PL of x is called the Lth Legendre polynomial. We also encountered Legendre polynomial in the previous chapter, so you can review also the lectures there. And that is the orthogonal polynomials in the interval -1 to +1, and they are generated by the Rodriguez formula, and the Rodriguez formula is this one here. So if you want to do some example, if you want to check this formula, you can just replace L with 0, and then you will get P0 of x is equal to 1, P1 of x is equal to x, P2 of x is just equal to 1/2 times the quantity 3x squared minus 1. You can solve that in your free time. And for the associated Legendre polynomial, you can also generate them. Here, look at this. If for the associated Legendre polynomial, if m is odd, which means this one m here, it carries a factor of square root of 1 minus x squared, this one. So if m is odd, so if it's not odd, it doesn't contain any square root. So anyway, going on, we actually had to convert the argument of the associated Legendre polynomial into cosine theta. So what we really need is this one here, and of course we have this identity. You can also use that like in this case, for example. And also PLM or PML cosine theta is always a polynomial in cosine theta multiplied by sine theta if m is odd. It's just the same as here. Your x is cosine theta, and it becomes 1 minus cosine squared theta becomes sine theta there. Note that PLM is equal to PL negative M. if you check the formula here, here, look at this expression. It has a absolute value of n. That's why there is an equality of PLM and PL negative n. So you have here some associated Legendre functions. There are quite a few. You have P11 is just sine theta, P10 is cosine theta, P1 negative 1 is also this one. Here is P2 2, and this is also equal to P2 negative 2. This is P2 1 and also equal to P2 negative 1. So these are just some of the associated Legendre function. Associated Legendre function has a subscript and a superscript, while the Legendre functions only have a subscript. You can check that out. We notice that L must be a non-negative number or non-negative integer for the Rodriguez formula, and if m is greater than 1, then let me check this one here, but I'm sure this one is I think there is some reason for this, but I will have to check this. Let's check it in the book. Okay, so if you have L equal to 1 and if m is greater than 1, PLM would be 0. So if you have, for any given L, the value of m could be from negative L to 0 or to negative 1, and then including 0, then you have 1 to L. So you have m values of L plus 0, and that's a total of 2L plus 1 values of m. So the volume element in spherical coordinates is this one here. We are cube r, that's r square sine theta dr d theta d phi, and the normalization condition would be given by this. And since your phi can be separated into products of radial and angular contributions, so your radial wave function would have separate integral multiplied to a separate integral of the angular um, uh, wave function, and that's just equal to 1. This is equal to 1, and also this one is equal to 1. So you have this, and you also have this one. Of course, when you integrate all of space, your radius should be from 0 to infinity, and your phi would be from 0 to 2 pi, and your theta would be from 0 to pi. And here, notice that you have an identity here. This one, the YL negative m is just equal to negative 1 to the m YLM conjugate. This is called the normalized angular wave function is called the spherical harmonic. You can check this out in the first few spherical harmonics that's given in this table 4.2 here. So you have for y0 0, this is that. For y1 0, this is the expression. So you will have cosine. Then looking at this one, there's a presence of exponential positive negative I phi here also, and here and here. When the superscript is 0, doesn't contain the exponential. If your superscript is not 0, it has an exponential I phi. And the spherical harmonics are orthonormal to each other, giving us this orthonormalization condition here, this one. So this is the conjugate part and the original part integrated with respect to d theta and d phi. It's just equal to Kronecker delta L prime and Kronecker delta M prime. So let's now go to the radial equation. So the radial equation would so here, if v is only a function of r or xyz, or it only affects the radial part of the wave function, that's r of r. Remember, psi rt or r, I mean phi phi r theta phi is just equal to r times y theta phi. So the potential only affects the radial part. This is now the expression for the radial part. We go back to this equation here. This is the radial part. Here, this is the radial part. And we go to that again. Here. So this is quite a complicated differential equation, but we can um, change variable to simplify it. We change variable into u, a function of r, where it's a product of r and the big function of r with respect to r, so that your big R will be u over r, and then your derivative of r with respect to dr would be this one, and then you will have this expression to be just equal to r differential, second order differential of u with respect to r. So your radial equation would reduce to this, which is much simpler to look at. And we have here an expression we call the effective potential, which contains a centrifugal term. So anyway, this is the effective potential. You can, this is, yeah, this one here. So the integral of u square dr should be equal to 1, as we have here, here, because u because r is just equal to u over r, so that the normalization condition would now be this one here. So we cannot solve the radial part without specifying the potential. So let's consider as an example, let's consider an infinite spherical well defined by this function v of r is equal to 0 if r is less than a, and infinity if r is greater than a. So outside the well, we have this, because you cannot find I mean, inside the well you have this one, because you cannot find the particle outside the well because the potential is very high. So the particle cannot get out of the sphere. And then here k is equal to square root of 2m e all over h bar. So if you have L is equal to 0, then this thing would be also equal to 0. And so your differential equation will look like this. And this is just the infinite square well that we solved in the previous lectures that we had. And the solution would be this one. You have a sine part and a cosine part. And of course, sine ka is 0, and k is of course equal to n pi in this condition. And your energies would just be this, where L is equal to 0. Okay? So if you normalize your UR, it will, normalization means U square dr is equal to 1, because you have your UR here, and you will find out that A is just equal to square root of, A is just square root of 2 over A. So we have a phi n 0 0, because your L is 0, and of course your M cannot have any value except 0. So your phi n 0 0 would be um, here, this one, sine n pi r over A over R. So now we look at the stationary states, and they are labeled by 3 quantum numbers: n, which is the energy level, and L, taken from the constant in the separation of variables earlier, and of course M, separation of variables in the angular part. So your phi is labeled phi NLM, and this is a function of R theta phi. The energy depends on N and L, this one here. So as you can see here, we're just taking the L to be equal to 0. Later on, we'll check if L is not anymore 0. For an arbitrary integer L, the general solution would be this form. It's not anymore sine and cosine. So the solution for this, for this one, the solution for this one is this one. Yeah. Where JLX is the spherical Bessel function of order L, and NL of x is the spherical Neumann function of order L. And they are just defined as follows here. JLX is defined as this one, and NLX is defined as this one. So you can see the difference. The NLX has negative sign as compared to this, and you have a cosine instead of a sine. So if you generate J1, J0, J1, N0, NL, and so on, you will have this. For J0, of x is sine x over x, n0 of x would be negative cosine x over x, j1, and of course n1 here. So those are the solutions if L is not equal to 0. But it, if L is equal to 0, you just have the ordinary sine and cosine. So for small x, for small x, the sine x would just be equal to this expression, and x cubed would be much smaller, and for cosine x, if you have very small x, this would just be the expansion of cosine, and for small x, this would become much smaller, and this one would be much smaller, so that your jo and j of 0 of x will reduce to 1. Yeah, here, because this is now equal to x, so x over x is just equal to 1, and cosine x will be just equal to 1, so that's 1 over x for your n0x. And you have the other j's and n would follow. Look at here. Bessel functions are finite at the origin. So at 0, this one is equal to 1. At 0, this is just equal to 0. But for the Neumann functions, at n0 of 0 is just infinity. It's not a number. So accordingly, for small x, our BL must be equal to 0 to neglect the n of L at small x. So our R would now have this form for very small x. So this one is equal to 0 for small x. So here are the first few spherical Bessel and Neumann functions, JL and NL. So now at R of A, the wave function should be equal to 0 since it's continuous at the surface. So beyond the surface, the barrier is infinite, or the potential is infinite, so it should be 0 at R of A, so that JL K of A is equal to 0. So here, Bessel functions are oscillatory. If we take a look at figure 4.2 here, it's oscillatory, but the amplitude is getting smaller towards infinity. So um, so but it recurs on points n or n pi. if you look at this figure, it oscillates in not in terms of 2 pi but in terms of pi, so that you will have this condition: k a is equal to b and l. By the way, I'm sorry for that. Look at this. We go back to the figure here. The first four Bessel function, spherical Bessel function. Look at the oscillation of this dashed line. It goes back to here. The points here, or the distance between this one and this one, is much farther. This one here is farther from here to here. They have different distance, so it's not like the period of 2 pi or period of pi. It's different. Although it oscillates, it changes amplitude. That's why you have you don't have a period, a constant period, so that you can just set ka is equal to some beta and L. And the beta and L here is the nth zero of the Lth spherical Bessel function. So your k would be equal to these are the zeros. These are the zeros here. So for this one, you have the zeros here, here, and here. So they have different. I mean, they're not really they don't have really constant periods. So um, so in this case, you have a k that is equal to, I'm sorry, a k that is equal to over a here. So now the allowed energies then are E NL equal to h bar over 2 ma, b beta squared and L, as opposed to k. So you will now have phi NLM to be of this expression. With NL here, you can determine that by normalization. So again, you should do this. NLM star r squared sine theta dr d theta d phi is equal to 1. So in this case, each energy level is 2L plus 1 fold degenerate, since there are 2L plus 1 different values of M for each value of L. So we have that. That's the end of the first session. So in the next meeting, we'll be studying about the hydrogen atom. We will not show in the lectures, we will not show the mathematical details of how the spherical harmonics, the Legendre polynomials are being arrived as a solution. We will just take them for us to move on immediately to the topics, because if we do it in more detail, that would take us so much time. So let's just assume that they're true, and I assume that's also taken up by your mathematical physics teacher. So anyway, that's all for this session. That's all for this class. The next class would be on hydrogen atom, and please take notes. Take some important notes on this lecture for you to answer the assessment that I will post in the Google Classroom. So stay tuned for that, and see you next meeting.